Simulating high strain rate deformations in aerospace components often stalls because the material subroutine is called millions of times per time step. These complex analytical laws create a massive computational overhead that hinders large-scale nonlinear analysis. Replacing standard analytical equations with neural networks converts branching logic into predictable matrix operations. This structural change allows for massive parallelization on graphics processing units, which is impossible with traditional conditional-heavy subroutines. The foundation of a neural material model is high-quality training data. Run thousands of small-scale representative volume element simulations to map various strain states to their corresponding stress responses and internal state variables. Standard grid sampling is inefficient for high-dimensional strain spaces. Use Latin Hypercube sampling to ensure the training data covers the entire operational envelope, including rare but critical loading scenarios like high shear or triaxial tension.
Neural networks are sensitive to the magnitude of input values. Normalize strain components and history variables to a range between -1 and +1 to prevent gradient vanishing issues during the training phase. For most constitutive laws, a multi-layer perceptron with 3 to 5 hidden layers is sufficient. Each layer should have 64 to 256 neurons to balance accuracy with the computational speed of the inference. Avoid simple rectified linear units for stress predictions, as they lack the smoothness required for derivative consistency. Use Gaussian Error Linear Units or hyperbolic tangent functions to ensure the resulting stress-strain curves are continuously differentiable. Standard mean-squared error is often insufficient. Implement a weighted loss function that penalizes errors in the tangent stiffness more heavily than errors in the absolute stress to ensure stable convergence in the global solver.
Neural networks do not naturally respect the second law of thermodynamics. Embed physical constraints into the network by using an architecture that satisfies the Clausius-Duhem inequality, ensuring that the model never generates energy during deformation. Plasticity depends on the loading history. Feed back the state variables from the previous time step as inputs for the current step. This recursive loop allows the network to track hardening and damage evolution over time. For complex history dependency, consider gated recurrent units. These specialized layers have internal memory gates that decide which parts of the strain history are relevant for the current stress state, ideal for viscoelastic materials. Graphics processing units have limited fast memory. Move the network weights and biases to the constant memory or texture cache to allow all threads to access them simultaneously with minimal latency during the evaluation phase.
The graphics processing unit performs best when processing thousands of points at once. Group all integration points from a block of elements into a single large matrix to maximize the throughput of the neural evaluation kernel. Write a custom kernel using the Compute Unified Device architecture. Avoid calling high-level libraries for each point. Instead, unroll the matrix vector multiplications manually within the kernel to eliminate function call overhead and maximize speed. Traditional subroutines use if statements that cause threads to wait for each other. Neural subroutines use the same mathematical operations for every point, keeping all 32 threads in a warp synchronized and fully utilized. Store intermediate layer activations in shared memory. This high-speed on-chip storage is much faster than global memory and allows threads to communicate and reuse data during the forward pass of the neural network.
Be careful not to use too many local variables in your kernel. High register pressure limits the number of active warps per multiprocessor. Keep your network small enough that the graphics processing unit can hide memory latency effectively. Using double precision is safer for convergence, but significantly slower on consumer graphics hardware. Consider using single precision for the neural network evaluation while keeping the global stiffness matrix and solver in double precision. Modern hardware features specialized tensor cores designed for matrix math. By aligning your neural network layer sizes to multiples of 8, you can trigger these cores to achieve a 5-fold increase in material evaluation speed. The solver requires a tangent stiffness matrix. Use automatic differentiation techniques within your graphics processing unit kernel to calculate the exact derivatives of the neural network with respect to the input strain, avoiding finite difference errors.
The Jacobian of the neural network is the material tangent. Evaluate this through backpropagation of the identity matrix. This is more computationally efficient than central difference methods and provides the quadratic convergence rates required for Newton-Raphson solvers. Integrate your model by creating a dynamic link library that the main finite element solver calls. The library should manage the device memory allocation and handle the data transfer between the central processing unit and the device. Standard memory transfers are a major bottleneck. Use pinned or page-locked memory for the strain and stress buffers. This allows the graphics processing unit to use direct memory access, bypassing the central processing unit and maximizing bandwidth. Use multiple execution streams to overlap data transfers with kernel computation. While the graphics processing unit is evaluating the current batch of points, it can simultaneously receive the strain data for the next block of elements.
Ensure your data structures are aligned to 32-byte boundaries. Misaligned memory access forces the hardware to perform multiple transactions for a single request, which can cut your effective bandwidth in half. To support different material parameters without rewriting code, implement just-in-time compilation. Compile the specific kernel for the current material properties at runtime to allow the compiler to perform aggressive constant folding optimizations. For materials like fiber-reinforced polymers, the network must account for orientation. Pass the orientation tensors as invariant inputs to the network. This ensures the model predicts the correct directional stiffness as the mesh rotates during simulation. Neural networks can extrapolate wildly outside their training range. Implement a safety wrapper that detects out-of-distribution inputs and reverts to a simplified linear elastic model to prevent the global solver from crashing.
Capturing the energy loss in cyclic loading requires the network to distinguish between loading and unloading states. Include the sign of the strain rate as an explicit input to help the model learn the hysteretic behavior correctly. Internal variables like equivalent plastic strain must be updated and stored. Design the kernel to write these updated values back to global memory so they can be retrieved as inputs for the next increment of the solver. Measure the accuracy of your neural surrogate by comparing it against a holdout test set from the high-fidelity simulations. Aim for less than 1% relative error in stress to maintain the integrity of the structural analysis. A valid neural material must preserve the quadratic convergence of the Newton solver. If you see linear convergence, check the implementation of your tangent stiffness derivatives for small coding errors or numerical precision loss.
Use the Insight Systems tool to identify bottlenecks in your implementation. Look for gaps in the timeline where the graphics processing unit is idle, which usually indicates that data transfers are not being handled asynchronously. Combine low-fidelity analytical data with high-fidelity experimental results using transfer learning. Pre-train the network on the approximate loss, then fine-tune it with small amounts of real-world test data for maximum accuracy. If the solver encounters a state the network was not trained for, trigger a subscale stimulation to generate that specific data point. Adding this to the training set creates an adaptive model that grows smarter with each simulation run. Ensure the runtime environment has the correct library paths for the Compute Unified Device architecture. Use static linking where possible to avoid version conflicts between the simulation software and the graphics processing unit drivers.
If the neural network architecture is static, use graphics processing unit graphs to launch the entire evaluation process with a single call. This eliminates the overhead of individual kernel launches for each layer in the network. For massive models, distribute the element blocks across multiple graphics processing units. Use peer-to-peer communication over the high-speed interconnect to share state variables without involving the system memory. Poorly conditioned tangent matrices lead to solver failure. Add a small regularization term to the diagonal of your neural tangent matrix to improve the condition number without significantly altering the physics of the material response. Run a single element test to compare the output of your neural subroutine against the original analytical code. Ensure that the stress and tangent values match within a tight tolerance before moving to full-scale assembly simulations.
By accelerating the material evaluation by 50 times, total simulation time can drop from days to hours. This rapid feedback loop allows engineers to explore a much wider design space and optimize components more effectively. While we focused on the Compute Unified Device architecture, the principles of neural material subroutines apply to other frameworks. Using cross-platform compilers allows your models to run on various high-performance computing architectures without rewriting logic. Many simulation tools rely on decades-old Fortran code. You can modernize these solvers by wrapping the neural network evaluation in a C wrapper, allowing the old code to benefit from modern hardware without a full rewrite. Treat your neural weights like source code. Store them in a version control system and document the training data used for each iteration to ensure traceability and reproducibility in a regulated engineering environment.
Replacing subroutines with neural networks is more than a speed upgrade. It is the key to unlocking multi-scale modeling, where microstructural physics are embedded directly into the global structural analysis through lightning-fast neural surrogates.